Hello, this video is on integrating e to the x and a to the x, basic integral functions to know, integrals of trigonometric functions, and how to integrate inverse trigonometric functions using substitution. So let's start with integrating. E to the x and a to the x. Here, e is the Euler number, and a is any number or constant. Integral of e to the x dx equals e to the x plus c, where c is another constant. We know this is true because you previously probably learned that derivative of e to the x to the x equals e to the x. But why is this true? Well, to prove the integral of e to the x, you need to first modify e to the x to another function that models e to the x. And one function that represents e to the x is as follows. E to the x equals 1 plus x squared over 2 factorial plus x to the 3 factorial, and on and on. This is called a series decomposition of a function e to the x. It is something you will learn to do in the future. For now, just trust me that e to the x equals this function. When we integrate e to the x, or integrate both sides of the equation sign, we get integral of e to the x equals integral of 1 plus x squared 2 factorial plus x cubed to the 3 factorial, and on dx. If we integrate both sides, we get that integral of e to the x dx equals x plus x over 2 plus x to the 3 over 3 factorial plus x to the 4 over 4 factorial, on and on and on. And then there's also a plus c at the back. As we can see, the original equation e to the x is identical to the integral of e to the x, and hence this is a proof that integral of e to the x equals e to the x. Now, if you're trying to integrate e to the cx, where c is any constant, then we know this equals e to the cx over c, and you can prove this by multiplying c to the series decomposition of e to the x and then integrating both sides. Now let's move on to integrating a to the x. Integral of a to the x dx equals ax over ln a plus c. Now, why is this true? Well, to prove this, we need to first modify the a to the x function. Ax equals e to the natural log of ax. We can move x forward so that ax equals e to the x natural log of a. Here we know a natural log of a is a constant, because a is a constant. And if you remember this equation here, the two are identical if you replace c with natural log of a. So then we can immediately know that integral of ax dx equals integral of ex to the natural log of a dx, which equals e to the x natural log of a, which equals e to the x natural log of a divided by natural log of a. Now we can move x back up so that we have e to the natural log of ax over natural log of a, which equals ax over natural log of a. Now, before moving on to the next topic, I just want to list a few common integrals that I recommend everybody to memorize. So here are some common integral functions. We have integral of sine x dx equals negative cosine x plus c. Integral of cosine x dx equals sine x plus c. Integral of secant squared x dx equals tangent of x plus c. Integral of cosecant squared x dx equals negative cotangent x plus c. Integral of secant x tangent x dx equals secant x plus c. Integral of cosecant x cotangent x dx equals negative cosecant x plus c. And we also have integral of 1 over square root of a squared plus x squared dx equals arc sine of x over a plus c. Lastly, integral of 1 over a squared plus x squared dx equals 1 over a arctangent of x over a plus c. There are also some common trig identities that you should memorize because all of the complex trigonometric integrals require you to know these identities. So common trig identities. We have sine squared theta over 2 equals 1 minus cosine theta over 2. Cosine squared theta over 2 equals 1 plus cosine theta over 2. Tangent of theta over 2 equals 1 minus cosine theta sine theta. Sine squared theta plus cosine squared theta equals 1. Secant squared theta equals 1 plus tangent squared theta. Cosecant squared theta equals 1 plus cotangent squared theta. How to integrate complex trigonometric functions. Integrate complex trig functions. So let's start with an example. Integral of cosine cubed x dx. What I would recommend you to do is when you see these cosines or sines with power of 2 or higher, you want to decompose the trigonometric function so that you have multiple cosines or sines to the second power, and then one cosine or sine depending on whether the original function is into the power of even number or an odd number. So in this case, we can decompose cosine cubed x into cosine x and cosine squared x. So we have integral of cosine x times cosine squared x dx. And here, what we can do is we can remember one of the trig identity and substitute cosine squared x with 1 minus sine squared x. So now our function looks like integral of cosine x dx minus integral of cosine x sine squared x dx. Now, I'm pretty sure you know how to solve this integral. But the second integral is a bit difficult to solve. We will be solving this integral by using the method of substitution. The substitution method works when one of the term in the integral is the derivative of the other term. So for example, let's call sine x u. Derivative of sine x is du, and du equals cosine x dx. So what we can see is that the cosine x term is the derivative of the sine x term here. So let's replace all sine x with u and cosine x dx with du. Then our function now becomes integral of cosine x dx minus integral of u squared du. Now this integral is easy to solve. So now what we have is this equals sine x minus u cubed over 3. Now we will substitute sine x back into u, so we have sine x minus sine cubed x over 3 equals the integral of cosine cubed x dx. Now let's try another example. We have integral of sine to the 4x dx. So now we want to decompose sine to the 4x to 2 sine 2x. So this function equals integral of sine 2x times sine 2x dx. And this equals integral of sine squared x, the entire integral squared, dx. Now, here we cannot use 1 minus cosine squared x to replace sine squared x because that would complicate this function. Instead, what we can do is we can replace sine squared x with 1/2 times 1 minus cosine 2x. Sine squared x equals 1/2 times 1 minus cosine 2x. Now, how do you know this is the identity we want to use for this problem? Well, as you can see, because we don't have another cosine x term at front of sine squared x squared, or another sine x term at front of sine squared x squared, we cannot use the substitution method because there's no du in this problem. So in that kind of situation, my suggestion for you is to replace the terms you have in your integral with another trigonometric term with a lower power. And as you can see, cosine 2x is only of power 1, where sine squared x is of power 2. So that's why this integral is, this trigonometric identity function is selected. So replacing this cosine function with sine squared x, we now have integral of 1/2 1 minus cosine 2x squared dx. This equals integral of 1 to the 4 minus 1/2 cosine 2x plus 1 to the 4 cosine squared 2x dx. We can do the same thing again to this last term, where we replace cosine squared 2x by another trig identity function, where cosine squared x, where cosine squared 2x equals 1/2 times 1 plus cosine 4x. Note, this equation comes from the identity cosine squared x equals 1/2 times 1 plus cosine 2x, except the x is now replaced with a 2x. If we have this function replacing the last term in our original integral, then now we have integral of 1/4 minus 1/2 cosine 2x plus 1/8 plus cosine 4x over 8 times dx. Now, each of these integral terms are easy to integrate. Now let's move on to talk about integral using substitution for inverse trig functions. Here we're interested in finding the integral of this kind of format: 1 over square root of a squared minus x squared, or 1 over a squared plus x squared. Let's look at an example. Integral of x dx over x to the 4 plus 2x squared plus 2. The denominator could be modified as such: x to the 4 plus 2x squared plus 1 squared minus 2, plus 2 minus 1. So that the denominator equals x squared plus 1 squared plus 1. Why did we do this? Well, because this denominator represents the denominator in this form. Why? If we replace a with 1 and x, or in this case, let me call this u, with x squared plus 1, so that du equals 2x dx. This gives us dx equals du over 2x. If we replace a, u, and dx with the terms found in the original function, then what we end up is integral of x du over 2x times u squared plus a squared. This equals 1/2 integral of du over u squared plus a squared. So what happened here? We modified the denominator so that we have one term in terms of x squared and another term in terms of a constant squared. As long as you can make the denominator in this form, then you are able to turn your function into the second format here. But how did I know that I can make it into this format by adding 2 and minus 1? What comes from practice. The best suggestion I can give for anyone solving this kind of problem is to practice, and practice. Because there is no one-step solution to finding how to modify the denominator so that you can have the denominator in this format. Now let's move on. So we have 1/2 integral of du over u squared plus a squared. If you remember from an equation, one of the trigonometric identities we listed above, this equals 1/2 times 1 over a inverse tangent u over a plus c. We can replace a with 1 and u with x squared plus 1, so that the final answer equals 1/2 inverse tangent times x squared plus 1 plus c.